Kia ora. Thanks for joining me today. I'm going to present a brief overview of work we did at EP Center to assess energy demand and greenhouse gas emissions from heavy freight transport in New Zealand. A few things that are worth highlighting from the title. The focus was on tank-to-wheel or direct emissions. However, to a lesser extent, we also did research on indirect emissions, specifically looking at the embedded emissions of fuel, vehicles, and infrastructure for different modes. We want to assess direct emissions from three perspectives, across modes and means of transportation, across commodity sectors, and across the transport network. Data in this project had a geographical component, often related to the movement of or flow of freight between regions. The focus was placed on road transport as it dominates the freight sector with 92.8 of total freight tonnage, and also due to data availability concerns. The project was aligned with the in-time framework, and I will explain briefly what this is in the upcoming slide. In phase one, we define and understand the present baseline. We aim to work in phase two, where we aim to assess the technical and economic feasibility of different technology and infrastructure options as part of a scenario analysis. Transport is a sector with the highest energy demand. The sector is heavily reliant on oil derivatives, as these fulfill 99.8% of national transport energy requirements. The New Zealand government has updated its determined contribution under the Paris Agreement, a reduction of 50% below 2005 greenhouse gas gross emission levels by 2030. It is imperative to identify strategies to support national commitments and reduce fossil fuel dependency. Our approach is aligned with the in-time methodology. As you know, it is a strategic framework to identify economic and technically viable changes that will enhance existing systems to maintain essential services while eliminating the dependency on the use of fossil fuels. Our project focused on defining the baseline. For freight transport, this translates to taking stock of transport activity, energy use, economics, and environmental impacts. Work was restricted by the quantity and quality of information. The reasons for the lack of freight data are owed to limited resources, different data acquisition standards across private and public organizations, heterogeneity of actors and commodities, and reluctance to disclose commercially sensitive information. Work for phase one was arranged into different parts or stages. During the data gathering stage, we identified and categorized the most relevant sources of freight data, which included regional statistics, geographic data, safety inspection data, and transport-related data. In data filtering, we developed a relational data model. The point of departure was a data wrangling process where data issues were identified, data was clean, and we defined consistent temporal and spatial scales across data sets. Some transformations were done in compliance with suitable transport modeling approaches, and I will talk about this in the upcoming slides. In the data integration stage, we defined a relational data model that fits with our data resources and can allow us to assess transport demand. There is also a visualization component, which comprehends the development of an online dashboard as a platform to interact with the data and results. In the final data interaction stage, the data was used to assess transport demand and map the energy demand and carbon footprint of freight operations across modes, vehicles, and transport network. This is a representation of the relational data model, which incorporates different resources which had to be cleaned to ensure the implementation of relational operations. That is, attribute values had to be consistent across data sets. Our main sources come from Land Information New Zealand, Pacifica, Swire Shipping records, New Zealand Transport Agency safety inspection records, and Ministry of Transport. One of the key sources of data was NZTA's inspection data. It consisted of 1.9 million observations of warrant of fitness and certificate of fitness records. Um, also, this this exercise involved data cleaning and filtering. It was an important challenge as most of the information behind this data set was inputted by hand. The main goal was really to estimate fleet numbers and vehicle kilometers traveled. Fleet numbers classified by year and country of manufacture are relevant to estimate embedded emissions. On the other hand, the vehicle kilometer figures were used to estimate emissions across different vehicle categories depending on their gross vehicle mass. We had to consider vehicles that are only used in heavy freight transportation. For the distance traveled, our estimates were based on habarometer readings, which is a regulated device that is installed on every truck in New Zealand. We have also built an interactive dashboard. The idea was to visualize the resources from the repository and also document our results through the dashboard. We wanted to make this process interactive, so it was easier to obtain estimates depending on criteria defined by users. For the transport modeling part, we aim to obtain a higher spatial resolution for the freight demand that is district by district basis. We also had to identify suitable locations to represent the origins and destinations of every trip. The model inputs were traffic count data, production and attraction attributes by district and by commodity sector and travel cost. The underlying principle of this model was that the estimated flow through a link is the summation of the contributions of all trips from all commodities. This way, we're able to estimate the origin destination matrices across different commodity groups. This is still a work in progress. We did not use this model to support emission calculations. Instead, this sort of a tool would be helpful eventually when trying to characterize the future freight task in New Zealand. After having arranged our data sources in the proper data structures, we can use energy and emissions modeling software to calculate energy use associated to road, rail, and coastal shipping. This is the last stage of phase one. Then we employed different software resources to translate freight activity estimates into energy and emission figures. For instance, the Sankey diagram shown here was obtained through a software called LEAP, which allowed to model the New Zealand energy system and track energy transformation processes from resource extraction to final consumption, hence allowing us to estimate well-to-pump emissions for different commodity groups. Another software package called COPERT, and this is the European software standard for calculating truck emissions. This software allowed us to estimate direct and indirect emissions for the heavy vehicle fleet. In this case, the advantage of the software was that of capturing operational aspects of the fleet like road slope, vehicle utilization, and circulation regimes. Finally, we use Grid software to evaluate embedded emissions of vehicles and infrastructure. These are some of the results obtained from our study. Some points I would like to highlight is the distinction between direct and indirect emissions. For instance, we found that most of a truck's lifetime emissions come from the fuel it consumes, approximately 80%. Another highlight is the contrasting estimates between the commodity-specific approach and the vehicle fleet approach, which served as model for model validation. From the figure, we can conclude that the utilization for the heavy truck fleet lies between 50 to 75%. In the case of rail, our results were contrasted against Kiwi Rail figures. There were some uncertainties in our analysis given assumptions that had to be made for the locations of origins and destinations for intra-regional flows. For shipping, a major challenge that we managed to overcome was that of estimating activity and emissions associated to ferry movements. Also, most of the flows are associated to general consumer goods, which are moved in containers. This information was obtained from Swire manifest records. It is worth highlighting that we use 2017 as a base year, hence the estimates account for uh, interregional petroleum movements as well. More results, and now comparing emissions across modes, it is clear that road transport is responsible for most of emissions from the sector and is significantly outperformed by other modes in terms of energy use and emissions. The plot with the gray bars compares carbon intensity for all modes. It is worth highlighting that coastal shipping has the smallest intensity, and to some extent, this is owed to the movement of petroleum products. We are aiming to continue working in this area. We're proposing to investigate different decarbonization pathways, including changes in resource conversion technologies and shifts to more energy efficient modes of transport. For the technology substitution option, the aim is to map different feasibility hurdles, technical challenges, material needs, and processing and system architecture and system integration that must be overcome along the development pathways for different technologies. For the modal shift option, we aim to use multimodal network analysis to evaluate the impact of potential shifts of activity from road transport to alternative modes. And finally, another gap in the research is the characterization of last mile freight logistics, which brings additional complexity. In this regard, we are proposing the use of passively collected data sources like GPS fleet records, mobile data, and firm or establishment data to map the transport logistics across different business models. I'm happy to take any questions. Thank you for your time. Good night.